Is it ready?
Oh, it's recording.
It's recording now. Thanks for telling me.
Yep.
All right. Shh, shh, shh. That is a skinny kid. I'm just going to make up a mass. It'll be a very skinny kid. I'll go with 30 kgs. Let's say he's on a pair of roller skates, 6 meters per second. Okay? Now, I know this is America, but let's pretend we can find a fat kid. With roller skates. Okay? So, fat kid, I don't know, 90 kgs, and he's not moving. So, when these two bang into each other, which is why you're following me,
Follow.
one of two things can happen. They either stick or they bounce. So I will do the math first. If they stick, then I don't know what it would look like. It would look, I don't know. Ish. All right? So if they stick, then they come together, they become one item, and what I would ask you is then their final velocity as they roll away together, which is why you're over here. Okay? So what you would say is the sum of the mo b-fo is the same as the sum of the mo b5 before and after. The mo before is the mass of the skinny kid times velocity of the skinny kid plus the mass of the fat kid times velocity of the fat kid. The fat kid's velocity is 0, so this whole term goes away, and then it becomes the mass of both of them together. The whole mass is what I jokingly call the mass whole times their velocity final. So, it's just the mass of the skinny kid times velocity is just 30 kgs times 6 meters per second is the same thing as 120 kgs times something. So what, 180 divided by 120, which is why we're doing the math.
1.5.
Thank you.
I said one, the fat kid, the skinny kid.
We say 1.5 meters per second, right? Simple? Huh? Because this is kg meters per second, this is kgs, you're left with a meter per second. Now that's if they stick. If I were to ask you how much mo does the fat kid have? You would say the mass of the fat kid times velocity of the fat kid. The mo of the fat kid, or the mass, I'm sorry, was 90. And I'll multiply that by 1.5. So the mo of the fat kid is what, 120, or no, 135, thank you. 135 kgm/s. What about the mo of the skinny kid then? This is the mass of the skinny kid times velocity of the skinny kid final. This is going to be, what, 30 times 1.5, which is 45 kilogram meters per second, which should make sense because 135 plus 45 is the same. It's 180. So again, the change is in mo. It's just like life that added up to nothing. All right, so that's if they stick. The other option is if they bounce. If they bounce, then it would look, I don't know, something about yay. Okay? All right, so what I would want to then ask you is one of two things. I'll either tell you the velocity of the fat kid and ask you for the bounce velocity of the skinny kid, Or I'll give you the bounce velocity of the skinny kid and ask you how fast the fat kid drifts backward. So I don't care. We might as well say, okay, the skinny kid bounces backwards. If he was going 6, it's got to be a number less than 6. So let's say his velocity final is, I don't know, 4 meters per second. All right, backwards, that'll become significant here in a bit. Okay, let's say he goes 4 meters per second backwards. All right? And so then the velocity final of the fat kid would be what we solve for. Hopefully, you can tell it's the exact same math, exact same formula. On the left side, nothing changes. It's still just the skinny kid plus nothing. But on the right side, hopefully you can tell they don't stick together, so we don't have a whole system, so I'm not going to have a mass hole here. I'm going to still have a mass of the skinny kid and a velocity, the skinny kid final, plus the mass of the fat kid times velocity, the fat kid final. And that'll be what we end up looking for in this particular question. So all I'll do is go ahead and put mass of the skinny kid times velocity, skinny kid final. The mass of the skinny kid doesn't change. It's 30 kgs. I'll multiply that by, again, we said 4 meters per second. Now, we said the word backwards. If it were English class, that would be sufficient. But how do you mathemologically communicate backwards is to put a negative. So please don't forget, if something is going in the opposite direction, you got to put an opposite sign there. So that's times -4 plus the mass of the fat kid was 90 kgs times some final velocity that our goal is. All right, so when we move this over, I will not push the minus button. I will push the plus button. So 30 times 6, we said what is 180? We're going to add 120 to that. 180 plus 120, which is what, an even 300?
Yeah.
Kilogram meters per second is clearly the same thing as 90 times some VF. I don't know either, but 300 divided by 90.
Which is 3.33.
Thank you. VF then is 3.33 meters per second. That's just the velocity, meters per second. So that means the fat kid, is he moving faster when they bounce or slower when they bounce?
Slower.
Very good, faster. It's okay. When they stuck, that's why I left the numbers up here, meters per second. When they stuck together, he was only moving backwards at 1.5 meters per second. When the skinny kid bounces, now he's moving backwards, the fat kid, at 3 meters per second. That's double the amount of mo change, because the change in mo of the skinny kid has to equal the change in mo of the fat kid. And the change in mo of the skinny kid went from 180 to -120. It's because +6 velocity to -4 in velocity is a change of 10, compared to if they just stick together, it was from 6 down to 1.5 or whatever. So that change in velocity is a lot smaller. It's only a 4.5 change, whereas here it's a change of 10, because 6 to -4 is a change of 10. All right, but anyway, that means the fat kid's going 3.33. If I ask you for the mo of the fat kid, it's 90 times 3.33, which is
299.7.
300-ish. Thank you.
You're welcome.
Kilogram meters per second. Now, that's more mo than the skinny kid had to begin with, right? But that means we're going to subtract some mo, because if I were to ask you for the mo of the skinny kid final, it's 30 kgs, but multiply that by his backwards velocity, which is -4, which is -120. So what's 30 plus -120? 180, which is the same as what he started with. So again, it's like life. The change is added up to nothing. So just remember that negative is how you communicate opposites. All right? All right, now, another question I could ask you is, if I tell you the amount of time the collision is, I can ask you the force that they feel between them. All right, so I'll keep it simple. What if this fat kid, they're in contact for 2 seconds? So there's a lot of squish time involved. A 2-second collision. All right? Then what I would ask you, since I'm dealing with times now, is how much force was exchanged between the fat kid and skinny kid. And so now if we're dealing with forces and times, we're going to use the impulse equation, which is just force times time is equal to the m delta v, the change in mole. So a force times time equals the delta mole. So you would pick one, and whichever one's mo you wish to calculate the change of. It doesn't matter. The change in mo of the fat kid, change in mo of the skinny kid. I would go with the skinny kid just because you know the numbers already. So to calculate the force, it's the change in mo divided by time. That goes away. The change in mo of the skinny kid is the skinny kid's mass, which is 30, times his change in velocity. A change in velocity is always a final minus initial v. So the skinny kid's final v, -4, minus his initial v of 6. So it's -4 minus 6, that's -10. So 30 times -10 is -300. We're going to divide that by, what'd I say, 2 seconds. So -300 divided by 2 seconds is the amount of force. It became a negative number because what direction the fat kid pushed him was in the opposite, backwards, negative direction. So 300 divided by 2, he felt 150 newtons worth of force in the negative direction. Okay? So that's when there's 2 seconds worth of bounce or of squish time. But what if this is a big kid, but let's pretend he's not fat. Let's pretend he's like me and he's chiseled. So the amount of squish time is not a full 2 seconds. I'll just keep it simple and say, what if that bounce occurs in 0.2 seconds? So that's almost an immediate turnaround. Then what would that change in the amount of force the skinny kid feels? Would it be more or lesser? And it would be more because our denominator gets smaller, and it goes from 2 to 0.2. So this is going to fit into there a lot more, and I think it just adds a 0, doesn't it?
Yep.
Yeah.
So exponentially bigger. So it went from 150 to 1500 newtons. So that's why they say, hey, when you bang into things, you want a lot of squish time. You want the increase in time decreases the force, and a decrease in time increases the force. And again, I use the skinny kid's perspective, but how much force did the fat kid feel? Same amount of force, right? So they both experience the same impulse. They both experience the same change in mo.
It would just be in opposite directions, right?
Yes, that would be a positive 1500 instead of negative 1500. Yay, physics.